In the last lecture, we were looking at the use of the two-stream equation to derive the reflectivity of a layer which is scattering. This could be a layer which is a layer of particles in insulation, or it could be a cloud layer, and the aim was to derive the overall reflection from this layer, and we had used the following equation. We had looked at the general equation for the upward intensities, and a similar expression for downward intensities. So, here we have two equations in two unknowns, and we can solve it. And the solution to the equation can be written in a very simple way in terms of one of the ways to define equation you can obtain is define a y plus or minus equal to I plus or minus I minus. If you do that, you got a single equation, second order equation, which says t squared y plus or minus by t tau squared is equal to tau squared y plus or minus. Now, this can be solved very easily, and the solution that you get will indicate that y plus or minus is equal to C 1 plus or minus e to the power of gamma tau plus C 2 plus or minus e to the power of minus gamma tau. So, this is a simple equation. Now, the real challenge is to find C 1 and C 2 and relate it to the equation. So, we can write in terms of I plus I minus, which is a more familiar form, is C 1 e to the power of gamma tau, C 2 e to the power of minus gamma tau, and I minus can be written as C 3 tau, where gamma is nothing but 1 minus single scattering albedo by mu square. So, we see that the intensity, the way it damps out, depends on this single scattering albedo. Is 1, there is no damping, and as the single scattering albedo goes below 1, there is more absorption. So, there is more damping. It also depends on the angle. If the angle is very large, there is more path length and there is more damping. So, we can relate C 2 to C 4 and C 3 to this one, and you will get that C 2 is rho infinity C 4 and C 3 is rho infinity C 1, and where rho infinity, as we will see later, is related to the overall reflectivity of the medium. And the boundary condition we need to use in order to solve for C1 and C4, now there are two unknowns, is that the upward flux at tau equals tau star is 0, that is the lower boundary is tau star, upper boundary is 0, we are assuming a black boundary. So, there is no reflection, and at the top the downcoming radiation is equal to I 0, incoming radiation. So, once this is done, you can solve for C1 and C4, which are the two unknowns in the equation, and you will get C1 as rho infinity into I 0 by rho infinity squared minus e to the power of 2 gamma tau star, and C4 as I by 1 minus rho infinity squared e to the power of minus 2 gamma tau star. So, this completes the total solution, but the final interest in this problem is to get an expression for reflection of this layer, which is scattering, and the transmission. So, so it is in terms of the ratio of the upward to downward flux, that is all it is. So, reflectivity of the layer is nothing but I plus of 0, the upward flux, divided by what is coming down, that is reflectivity, and this you can write as rho infinity E gamma tau star minus E gamma plus or minus tau star divided by E gamma tau star minus rho infinity squared E minus gamma tau star. So, this is an expression for reflectivity, and you can look at various limits of this expression. If you recall, gamma was related to the single scattering albedo. So, the single scattering albedo is 1. So, gamma squared, if you recall, was 1 minus omega by mu squared. So, if omega tends to 1, then gamma tends to 0. So, gamma 0 in these things, of course, the R layer would tend to 0, but you need to be careful here. You have 1 minus rho infinity here, but you have 0 on the top. So, the layer will not reflect here. So, now let us look at the other limit when the gamma optical depth of the layer is very large. We can think of a semi-infinite region, then this term will drop out, this term will drop out. So, if tau star tends to infinity, you see R layer tends to rho infinity, which is not surprising, but that is why the term 1 omega mu squared was related to gamma, and we define rho infinity, if you recall, in terms of the single scattering albedo. So, that we so rho infinity, which is nothing but 1 minus root omega by 1 plus 1 minus root omega. So, single scattering albedo is 1. So, rho infinity tends to 1. So, in the optically thick limit of this layer, single scattering albedo is the only parameter that influences the result, and the optical depth itself is not that critical. Similarly, one can look at the transmittance of the layer. It will come out as 1 minus rho infinity squared by e to the power of gamma tau star minus rho infinity squared minus gamma tau star. Again, you see here in the limit as the transmittance is very large. Of course, the tau star becomes very large, then the transmittance goes to 0. That is not surprising. But when the tau star tends to 0 here, then you have an interesting issue, which is that the layer transmittance will tend to 1. That is because this term goes to 1, this term goes to 1, you have 1 minus rho infinity squared, which. So, in the optically thin layer, of course, transmittance has to be 1, that is not too surprising. Let us look at the other case where tau star tends to 0 on the top. We saw that the R layer tends to 0, which is a bit surprising, but what we can do is we can look at the second order term here, 1 plus x minus I, you will get 2 gamma tau star, and at the bottom you will get 1 minus rho infinity, and so the 2 gamma tau star term will play some role. So, it is not completely negligible term. Now, one weakness of the derivation that we are just now done is that we have assumed G to be 0, that is, the asymmetry parameter was assumed to be 0, and that can be a serious limitation in cases where the scattering is not symmetric. So, now let us look at how we get the result modified when you include the effect of asymmetric scattering. Okay. So, we extend the result we just now derived to asymmetric scattering, and what asymmetric scattering does is only a minor modification to the basic equation. So, a basic equation now, assuming mu to be half, one minus omega I plus, and the big difference comes here. We have a G factor, which was missing in our previous derivation. So, it is worth noticing that G was 0 in the original analysis. So, it looked different. Here G is non-zero, and the second expression involves the asymmetry parameter also. So, there are two equations in two unknowns, but they are coupled because I minus appears in I plus equation and I plus I minus. So, you want to eliminate them, or you can combine them like last time and get the expression for I plus I minus, and it comes in just adding these two equations. And you will get it as 1 minus omega g into 1 minus omega into I plus I minus. So, you are getting now a single equation for I plus I minus, and we can get a similar equation for the I plus minus I minus. So, we do not write it down because similar. So, the solution to the equation is I plus will come out of the A e to the power of gamma tau plus B e to the power of minus gamma tau. Now, gamma is little different from the previous when you had 2 square root of omega 1 minus omega g. So, the asymmetry parameter is coming in here, which was missing in the last derivation. Then, as before, we relate C to A and B to D. So, those are essentially quite common, and where R infinity now will be So, again I want you to notice the difference between the previous derivation, which involved symmetric scattering, to here which is asymmetric scattering. Here g is not equal to 0. So, you get an expression where if you put g equals 0, you recover back what we did in the last derivation. Now, the next step, as in the previous exercise, is to use the boundary condition and derive expressions for reflectivity and transmissivity. That is the same logic as before. And so, let us now assume the used boundary condition, which is that I plus at the bottom of the is equal to 0, black surface, and I minus at the top is equal to I 0. Essentially, what we are saying is we have two plates, we have I 0 coming in at 0, and at tau star there is no reflected radiation, because this is black. So, that is the assumption I am making. Once you do that, the expression for I plus comes out as R infinity I 0 by e to the power gamma 1 tau star minus R infinity squared e to the power of minus gamma tau star into e to the power minus gamma tau star minus tau minus gamma tau star minus tau. So, this expression I plus. Now, notice that when omega equals 1, in the previous expression I will go to omega equals 1, this term drops out, this term becomes 1. So, omega equals 1, R infinity equal to 1, irrespective of the value of g. So, that is a new insight, which is that if the single scattering albedo tends to 1, that means the medium is non absorbing, then the R infinity value, which is a measure of reflectivity of the medium, the limit of very thick medium, does not depend upon the asymmetry of scattering. So, this result is surprising, but what it implies is that in the limit of a non-absorbing medium, it does not matter how the scattering occurs, either symmetrically or asymmetrically, ultimately all the photons have to emerge at the top. Now, similarly, when you take symmetry parameter equal to 1, means primarily forward scattering, you find R infinity is 0, irrespective of the value of omega. Again, this is interesting, does not matter what the single scattering albedo is, as long as most of the scattering is in the forward direction, then there is not much chance of back scattering or reflection back. So, that will tend to 0. Now, some of the results we obtained here can also be looked at in terms of figures. Now, here is the albedo or the reflectivity of a semi-infinite cloud, that is tau star is very large. As a function of the single scattering albedo on the x axis on a log scale, this is a log scale here, and R infinity is this parameter. Now, what you notice clearly is that, let me just write one expression here. So, R infinity here is very important, because this is nothing but I plus of 0 by I minus of 0. That is the albedo of the scattering layer. So, that is why we are looking at that expression. So, now this quantity, the albedo of the cloud of particles, as a function of the single scattering albedo for two different asymmetry parameters. One is 0, which is nothing but symmetric scattering. Other is G equals 0.85, which is primarily forward scattering. So, what it says is that when the single scattering albedo is below 0.9 or actually 0.99, the albedo of the cloud is very sensitive to the value of G, that is the asymmetry parameter, and when you go from symmetric to asymmetric scattering, the albedo can go down from 0.5 to 0.1. It's a huge difference. But as you go to very high single scattering albedo like 0.99 or 0.49, so you can see that it does not matter whether the scattering is symmetric or asymmetric, because ultimately you are reaching the value of 1. So, it is quite clear that whether the scattering or symmetric asymmetric is only crucial for those clouds of particles wherein the single scattering albedo is less than 0.9, then you can see there is some difference. So, if you have medium with a very high single scattering albedo, then you do not have to worry about the scattering being symmetric or asymmetric. But in most real situations where there is some absorption in the cloud, then you are going to be somewhere in this regime, and you can see here there is a large difference between the albedo, which is around 0.05 for asymmetric scattering, to around 0.35. So, there is a decrease in the albedo of the cloud by a factor of 7 as you go from G of 0 to 0.85. So, this must be kept in mind, that the single scattering albedo is a very important parameter in this situation. Now, let us look at transmittance. The transmittance you do expect it to go down as the optical depth of the cloud increases. So, this goes down as the optical depth increases, but the way it goes down is sensitive to the single scattering albedo. When the single scattering albedo equal to 1, it goes down in a certain way, but if it is 0.9, it falls much more sharply. This is not surprising, because at 0.9 there is a lot of absorption is going on. So, naturally the transmittance rapidly drops to 0 by the time you get tau star of 10, while in the case of the single scattering albedo being 0.999 or 1, the absorption is not playing much of a role. Now, next we look at albedo of this cloud, and you see that the albedo of the cloud is dependent on the cloud optical depth, not surprising, and the signal scattering albedo. And you see that when signal scattering albedo is 1, of course, it requires only the optical depth to be of the order of 40 to 50, that is also almost reaching the asymptotic value, while for more absorbing cloud layers with, let us say, omega of 0.9, you see that the albedo reaches very rapidly a value around 0.2 at optical depth of around 5. So, in absorbing cloud, the assumption of semi-infinite cloud is valid even for optical depth around 5, because most of the photons are very quickly absorbed, and it does not require much thickness of the cloud for it to behave like a semi-infinite cloud. While when there is no absorption, in this case, you require a thickness of the cloud of the order of 50 or 60 to get an asymptotic value of a semi-infinite cloud. Next, you look at the absorptance of the cloud, how much radiation absorbs. Of course, omega is 1, there is no absorptance, so we do not have to worry about it. But even when omega is 0.9 here, you can see that the ability of the cloud to absorb radiation reaches a maximum value by the time we reach 10 or 15, and after there is no change. Okay. So, this again is an indication that clouds which have absorption, they do not have to be extremely thick before they behave like semi-infinite clouds. Now, this graph shows the minimum thickness required to declare a cloud as semi-infinite as a function of the signal scattering albedo and the asymmetry parameter. When G is 0, that is the scattering is symmetric, you can see that by the time you have signal scattering albedo 0.999, you have reached a thickness of the layer of 100 for you to consider the cloud to be semi-infinite, while if it is only 0.9 as you saw earlier, it requires only a thickness of 4 or 5. And you can see that the asymmetric reflection causes the need for higher optical depth for it to declare semi-infinite. So, the asymmetry parameter does play a role in determining how thick a cloud should be before it can be declared as semi-infinite. Now, before we go further, let us also look at the non-absorbing cloud in some depth, and the non-absorbing cloud that we are dealing with here, where omega is equal to 1, that is consideration we have, then the reflectivity and transmittance can be written down in fairly simple manner. So, you have a non-absorbing cloud which means omega equal to 1, and then you can define the reflectivity of this cloud as being equal to 1 minus So, again one can see that unless the cloud is extremely thick, reflectivity will not go to 1, and the transmittance will be 1 by 1 plus so once more you see the a fairly strong impact in the non-absorbing cloud of the asymmetry parameter. It has a huge role to play. If G is 0, you get a simple result, and as G tends to 1, you see that the phenomena is somewhat more complicated. For example, for R, G tends to 1. G tends to 1, R tends to 0. Now, this is not surprising, because we recall that G tends to 1 only encourages forward scattering. If there is a lot of forward scattering, there will be no back scatter. So, you cannot expect any rays to come back on reflection, because most of the scattering is occurring in the forward direction. Now, we have seen how you can solve for reflectivity, transfer absorptivity of a layer based on basic properties of the particles in the cloud, and those basic properties are the asymmetry parameter, the optical depth, and the single scattering albedo. Now, let us presume that this information is available, and we want to understand the total transmittance of the layer. Okay. So, this is done very simply in terms of ray tracing, but we will also show that although ray tracing is physically a very meaningful method. So, we have, let us say, a layer of glass whose properties are known. So, a unit radiation comes here, that is intensity, and on the first phase it reflects rho back into space. Once it does that, you should recognize that whatever is not reflected will go on, transmitted, and by the time it comes to the second interface, so what is not reflected and absorbed is transmitted. It comes here. Once it comes here, it gets reflected, and so once it comes, it gets reflected. Now, this term has to be rho into 1 minus rho into tau squared. It has gone through this twice. And finally, when it comes out here, escapes reflection here, this will be rho into 1 minus . Now, this can be repeated many times. So, we have infinite series of reflection terms, and the expression for net reflectivity of all these comes as that rho, first term, and the common term here is 1 minus rho squared tau squared. This is quite understandable, because anything which goes back up has to go through this layer twice. So, that is tau squared, and has to escape reflection at the two interfaces. So, it is 1 minus rho squared. But then there is infinite series, which can be written as follows. So, applying the summation of series rule, finally, you get the rho infinity as rho So, this expression for the overall reflectivity of the layer, I will call it net. So, there is no confusion with the infinity which we had used earlier. I will call it net reflectivity of the layer in terms of reflectivity at each interface and the transmittance. Similarly, one can derive a net transmittance which will come out as tau Now, let us examine these results which have been obtained by ray tracing. Ray tracing is physically very satisfying and a simple approach, but it is important to recall at this stage that in ray tracing, especially if there are a large number of rays, it is easy to neglect or ignore some term. So, it is not guaranteed that everyone will get this expression. So, there can be mistake, there can be terms are missed out. So, it is good to be able to check this result. For example, let us see what happens if the layer reflectivity tends to 1. So, this term drops out and rho net tends to rho. On the other hand, if the optical depth of the medium becomes very, very large, we get a more complicated expression here. This term becomes very large, this drops out, tau square cancel out, and your total reflectivity will be a function only of the interface reflectivities. If you look at transmission, as reflected gets to 1, that is not surprising that transmit tends to 0, because these particles are trying to get reflected backwards mostly, and ultimately the amount of energy transmitted through will go to 0. So, this result is useful. It is also good to see an expression for absorptance. And you can see either rho is 1 or tau is 1. In either case, absorptance is 0, which is not surprising. If the particles in the medium are reflecting perfectly, then there is no impact, or the transmittance tends to 1, then of course, absorptance is 0. If all the photons are transmitted, then absorptance cannot play a role. So, overall this simple model does give us insight about the nature of this process, but it is important to recognize that although ray tracing is a very powerful tool, it is possible to make some error now and then, because one did not account for some stream. So, although ray tracing is very popular and very often used, but in actually doing a problem, if you desire to adopt ray tracing, one should be really clear that there is no one or no object which is interfering with the path over which you want to make the measurement. So, that question has to be kept in mind before you can adopt for this kind of approach. Now, although we did get enough insight because of adopting ray tracing, it is important to recognize the fact that there could be alternative ways of deriving the layer mean functions in terms of individual interfaces, and the best way to do it is what we had done a long time ago using the radiosity method. So, in the radiosity irradiance method, which we had already adopted when we are dealing with shape factors, we do not want to follow individual ray. We only want to know the impact of the total number of rays in the system, and so we do not do individual counting, in which case you can get some mistakes. So, we merely use this layer as a black box. We assume intensity coming here is 1 and this surface 1, this surface 2, surface 3 and surface 4. And the schematic we are going to employ is, we are going to assume that incoming radiation is 1 and outgoing radiation is B 1. Incoming radiation to 2 is Q I 2 and what is going out is B 2. Now, I want to use Q I 2 as notation. I want to follow whatever we used earlier. So, I will use H I or H 1. This is H 2 because the other one is H 1. So, the advantage now is that the radiosity B 1 here has to be equal to what is reflected already times H 1 which is 1 in our case by notation plus so the second term of this equation is 1 minus rho so, we write this as rho H 1 and H 1 is 1 minus rho into H 2 this one and this becomes rho plus. Similarly, for B 2 the second term is rho into H 2. And so, we write expression for also B 3 and B 4. So, this H 1 is 1. So, this becomes 1 minus rho plus rho B H 2. Okay. So, we are able to write B 1 in terms of H 2 and B 2 also in terms of H 2, but we need two more expressions and they are B 3 which is rho times H 3 plus 1 minus over times H 4 incoming radiation, and since there is no radiation coming from below, H 4 is 0. So, this becomes Similarly, you can B4 is nothing but 1 minus rho times B3. Oh, sorry, S3, I am sorry. So, now we have 4 expressions for the 4 radiation, and now you can calculate the various terms involving net radiation. First, you solve for the radiosities, and then we will look at how to calculate the. So, if you solve for all the 4 with 4 equations, you get B2 will solve to be for B3 and B4 is so we have solved for B1, B2, B3, B4, and the transmittance of the layer is nothing but B1, because B1 is the radiation leaving the surface, is B1 by H1 really, but we have taken H1 as 1. So, the transmittance comes out as nothing but tau into 1 minus rho squared transmittance is B4. So, transmittance is nothing but B4 H1. So, that will come out as this one. So, this result is not surprising. If the reflectivity of layer is 1, then of course, there is no transmittance, or the transmittance of the layer is 0, then there is no transmittance. Otherwise, this is very simple. Then what is the absorption of the layer or layer reflection first, or layer will come out as equal to B1, that is the expression. And there also can see that if the transmittance of the layer becomes very small, this term drops out, this term drops out, and we get only the first interface reflection. That is not surprising. The second interface, so this interface plays no role if the tau is very small, that is not much radiation comes to this point to reflect here. So, that is the message from that figure. Now, we finally look at absorptance. And that will be nothing but whatever radiation is there inside 2 and 3, and out of which this much is absorbed, and this is 1 minus rho into 1 minus tau divided by 1 minus rho tau. So, again you see that the layer absorptance is 0 if reflectivity is 1, or so if rho is 1 or tau is equal to 1, absorptance of the layer is 0. So, perfect reflection at the top interface or almost perfect transmittance implies there is no absorption in the medium. So, we saw that although the same results are also obtained from ray tracing, and physically it does provide more insight, but the more elegant way of deriving the layer properties is from the application of the radiosity radiation methodology we developed earlier lectures, because that is very easy to apply and it involves no bookkeeping, where you keep track of all the photons little harder. So, generally one would recommend for a new complex system, we adopt this radiosity radiation approach rather than actually doing the ray tracing. Of course, for verification of your result, you might want to do ray tracing just to verify the answer is correct. Now, these results that we have derived in today's lecture are very relevant for solar collectors. Solar collectors are typically two interfaces here, and so the net absorptance, transmittance and reflectance layers is pertinent. And if, for example, one finds the reflectance of the solar collector is very large, one can add a thin coating to reduce the reflectance in both layers. So, these are now routinely done in many devices, because thin coating does not fundamentally alter the transmittance of the medium, but same time reduces the reflectance, and hence more radiant sun gets through the glass plate into the absorber. So, this calculation will help to determine how much additional energy you will get in a solar collector, because using thin coating. And finally, one does an economic analysis to determine whether the additional cost of the coating can be balanced by additional solar energy collection. So, if we can demonstrate that by using this coating, you are increasing the solar energy absorbed the collector by 5-10%, then you can easily estimate what is the payback period for that coating that you are using. Now, this coating idea is also used in cameras, of course, to increase the amount of photons that get into your camera and into the film or your sensor. So, in the case of camera, this thin coating is very important, because if you want to do the photography in low light conditions, you will need every photon that is coming from the scene into your camera to be used and not to be lost by reflection or absorption. So, most camera lenses use coating to reduce the reflection, and the reduction in coating depends on this factor which we had seen earlier. So, if the refractive index of the glass is 1.5, this quantity can be quite large. And so, if you replace 1.5 to 1 transition to, let us say, 1.5 to 1.25, 1.25 to 1, a thin layer with the refractive index in between glass and the air, then you reduce the reflectivity of that layer. And this logic can be extended, and there are coatings which will continuously decrease the n value from 1.5 to 1 in this coating. So, this is a coating wherein they can reduce the refracting index gradually by putting series of deposits of reducing refracting index. So, this is now being routinely used in many industries like camera and collectors and so on, where loss of photons by reflection is to be avoided. Now, in the next lecture, we will proceed to look at Monte Carlo methods, which are the methods we will use if we want to deal with complex systems. Whatever system we discussed so far have been very simple systems, wherein simple methods are used. Now, if we have complex techniques, then we have to go to Monte Carlo.